This is Dr. Zhongran Li from York University, and the talk will be about bistatic remote sensing method for observing surface properties using reflected GNSS signals. Is your co-I also here, your advisor also here in the meeting?
No.
Okay. Do you want to, can you maybe give a short introduction about you, where you did your PhD and so on?
Yes, I'll do that.
Okay.
My name is Junchan Lee I'm in the York University since December 2017. I'm working with the Regina Lee and Sunny Business in York University professor here. So I studied about the physics in KAIST Korea. So my research subject was the ionospheric ionosphere measurement using the satellite payload. So these days I'm working on the similar project with the name of the GNSS reflectometry. So I'm prepared that kind of subject today. Shall I start?
Yeah, so are we recording? Yes, right? Yeah, okay. Yeah, then start your presentation, please.
Okay. Wait, did you see the presentation?
Yes.
Yes, let's start. So, as I say, my name is Junchan Lee. So, today I'm going to talk about the bistatic remote sensing method using the GNSS reflectometry. So, this is very similar research with similar presentation that I did in summer workshop in this year. So maybe this is the little bit more and more serious. This presentation will be more theoretically, and then I hope this research help you are knowledgeable about GNSS reflectometry. So here is the content. So I'm starting with what is the GNSS reflectometry, and then talking about the theory inside of the related with this research, and then I'm gonna talk about our current research project. So GNSS is the simple name to stand for the satellite navigation system. We already know about the GPS, which is developed by the USA. So and then GNSS is the representative name of to stand for this kind of every satellite. So GPS made from the USA, GLONASS made from Russia, and then Galileo from EU, and Beidou from China. So basically, this satellite have the purpose of to calculate the position and velocity and time of the receiver. So our cell phone already have this kind of device inside of cell phone, but this GNSS signal is the electromagnetic signal, so we can use these signals to measure the other parameters on the Earth. So two famous remote sensing method. There is two famous remote sensing method. One is called radio occultation. The other called is reflectometry. Radio occultation uses the reflection phenomena in the physics, and reflectometry uses the reflection phenomena about the physics. Then we can talk about more about the GNSS reflectometry. So this is first proposed by the Martin Naylor in 1993. In his research, he proposed to measure the ocean roughness using the Paris project. So the direct signal from the GNSS satellite have the right-hand circular polarization. So when the signal reflected on the surface, it has to change their polarization and time, and then little change about the frequency. So we in GNSS reflectometry, we will measure the direct signal and the reflected signal and compare both signal to see the difference of the frequency and time characteristics. So and then we can figure out that what is the property of the reflection boundary. Using this method, we will apply in various we will apply in various fields. So one famous example is the altimetry, which is to calculate the height of some mountain or the other places on the land, and then ocean roughness, and then we can get the wind and snow thickness. So, but in this project, in this talk, in also in my research, we are focusing on the soil moisture. Here is the here is the this figure shows the previous researchers' work. So from the beginning, there's using the GNSS reflectometry, some scientists predict the hurricane, and then also we can also measure the soil moisture using the GNSS reflectometry, and then altimetry. We can also use the GNSS reflectometry for calculate the ocean roughness. And then this is the characteristic and the advantage of GNSS reflectometry. Since we will use the free signal from the GNSS satellite, so we don't need any transmit satellite. So we just need to build some receiver on the surface, so it can call the biostatic system. And then this biostatic system can make our receiver, can our system to have very low cost and then low power, and then it can make it can build another it can make other receiver in simultaneously, so it may possible to measure in different place at the same time. So and then we only need the receiver of the GNSS. We only need the receiver, so we can put receiver on various kind of the platform. For example, we will put our receiver on the tripod and UAV, or we will put our receiver on the nano satellite as well. Then why do we need the GNSS reflectometer for exoplanet? So my answer is the GNSS reflectometry is also one method of the remote sensing. So if we found some other planet in the universe, we have to measure or exploring before to enter the planet. So we already have another method for remote sensing. The one famous remote sensing method is the SAR, which used the backward scattering method. But the disadvantage of SAR is their disadvantage is low resolution, because they only use the backward scattering signals from the satellite. So they have the limitation. They have limitation resolution. So comparing with the satellite, the GNSS reflectometry used the forward scattering method in electromagnetic scattering. So the GNSS reflectometry can measure various range of incidence angle using the various range of incidence angle, and then it will make the it will make more knowledgeable. Yeah, it will make our knowledge become growing about the exoplanet. So, and then the developing price will be very lower than the star mission. So I think the reflectometry is very useful. Will be very useful device for exoplanet. If we measure the reflected signal using the GNSS reflectometry, the delayed Doppler map is the fundamental output from the signal from the receiver. Delayed Doppler is the two-dimensional image using the delay axis and Doppler axis. So when you see the left-hand side of figure, we can draw the. Here is the in left side figure. This is the structure of the structure of this phenomena. So the white dot in the middle of the figure means the specular point. This is the point that has the same instance angle is same with the reflected angle. So surrounding this point, you can draw the ellipse, which is called isodoppler frequency line. It has on this line, every Doppler frequency has the same value. And then let hyperbola line is called iso delay line. Also, this line has on this line has the same value of the delay value, same value of delay. So using these two lines, we can draw the two-dimensional pixel, and then we can project the value of each pixel to the delay and Doppler axis. So here's you can show the example of delay Doppler on the right figure. Then, but in the scattering theory, there are two types of scattering. One is called coherent scattering. The another called is the incoherent scattering. Coherent scattering is coherent scattering is when the instance signal from the GNSS satellite, when the signal came from the GNSS satellite, the reflected angle is very similar with the instance angle. This is the definition of the coherent scattering. And then the other thing is called incoherent scattering. So in incoherent scattering, the reflected angle is very different with the incidence angle. So in GNSS reflectometry, the researchers trying to figure out what is the property of the coherent and incoherent scattering, and then trying to get the property of the surface using either scattering method. So on the top, you can show some dot graph. So this is the graph to calculate graph from the Cygnus satellite, which have the purpose of predict the hurricane. So using this data, we can calculate the coherent scattering parameter, and then we can calculate the soil moisture as well. You can see the example of this application. Then, as you can see, using the GNSS reflectometry is the soil moisture. The soil moisture can get very similar with the in situ measurement data. Also, there are one famous equation built by the Dr. Zabaratoni and Borovitz in 2000. It's called the bisatellite equation. So using this equation, the below the equation, the bottom side of the slide. So using this equation, we can model the bisatellite coefficient. So and this equation used for calculate the ocean roughness. So here is but the in front slide, the scientists assume that the signal only came from the in previous signal. The scientists assumed that the signal has the only one line, but in reality, the signal composed of a lot of number of signals. So as you can see, the top figure is our identical signals, but in reality, we can measure the signal looks like the below bottom. So the in so in our delayed Doppler in to model our delayed Doppler, we need more theoretical approach rather than the previous model the previous model that I shown, such as the coherent wall in Coulomb scattering. So in this group, we are trying to calculate we are trying to improve the electromagnetic scattering theory. The Kirchhoff approximation is the famous electromagnetic scattering theory. And then, but this theory is used in every other remote sensing community. So, for example, SAR community also used the Kirchhoff approximation. And then I heard that on the planetary community used the Hager-4 method that is very similar with the Kirchhoff approximation, and to calculate the bystander radar coefficient. So in GNSS reflectometry also use this Kirchhoff approximation, but the different thing is the SAR community use this approximation only for the backscattering phenomena, but we have to know the solution, or we have to build the mass, this theory from the to fit it in the forward scattering. So currently in our group we trying to calculate that kind of this phenomena as you can see in this slide, but this project is still going on. So if I have some time later on, I will show you about this result. And then these days, in this slide, I can show you this day's project in our group. So we call YOX GNSS receiver. So we are in the 3 years project funded by the Canadian Space Agency. Then our project title looks like the technology demonstration of soil moisture monitoring. And then currently we have built the prototype receiver using the commercial part, as you can see in the figure. So the bigger PCB is the evaluation kit of the FPGA. The smaller PCB in the figure is the RF front end evaluation kit as well. So we built this prototype receiver, and then trying to get the reflected signal, and then using that signal we will try to calculate the soil moisture on some surface. And then we also use the dual polarized antenna. So I said at the beginning of the presentation. So I said in the beginning of presentation, I said the reflected signal has changed their polarization from right-hand circular to left-hand circular. But in our project, we will measure the reflected signal has the right hand and left hand circular polarization. So we used the dual polarization antenna, having the property looks like in here in both directions. So, and then yeah, here is the antenna property. We bring our antenna and prototype receiver on the top of the Petri Science building in York University to try the initial test. So we put our receiver on the tripod and then measure the direct signal and reflected signal. Here is the example. Here is the one result which we can get from the initial test. So on the left side here, those are the fundamental property when the receiver working as a GNSS just receiver. Then it means that the acquisition and tracking is the basic fundamental property which the every GNSS receiver has to do. So on the left figure, you can show that we can say that acquisition and tracking, the receiver working very well in the acquisition and tracking algorithm. So we can find some satellite on the Earth, and then on the right figure you can show the 3-dimensional and 2-dimensional delay Doppler map. So it looks very similar when I presented on the previous slides. And using this delay Doppler map, here is our data product algorithm. So if we capture the electromagnetic signal using the antenna, using the front end, we sample the reflected and directed signals, and then these sampled signal will go to the acquisition and tracking part, which can be done inside of the FPGA on the front end, on the evaluate prototype receiver, and then as you can see, we can using the post-processing method, we can calculate the reflection geometry and delay Doppler map, and we will use these two parameters to calculate the soil moisture contents. But to calculate the soil moisture contents, we have to know what is the property of the soil moisture. So in 2098, the Dr. Harley find out that the dielectric constant of the soil is related with the soil moisture. So in this graph, you can show in his paper, he measured the dielectric constant and soil moisture using the reflected microwave signals. So in this graph, you can show some positive relation between the dielectric constant and the volumetric soil moisture. So in this project, with this evidence, in this project we will measure the dielectric constant first. So, and then using this dielectric constant, we will have conversion from the dielectric constant to the soil moisture. And here is our proposed method. So the GNSS reflectometry is a kind of new science. So there are many room to be developed. So one is for the predict the dielectric constant. So no one has to develop the dielectric constant and the soil moisture model in the GNSS reflectometry. So these days our group tried to propose some quantitative method to calculate this dielectric constant, and then we wanna build some model from this dielectric constant, the quantitative dielectric constant, to soil moisture. So using the direct signal and reflected signal, we can calculate the reflectivity, as you can see in the first line on the first equation on the slide. And then it is well known that the Frenet coefficient is related with the reflectivity that we calculated previously. So then using some analogy, the so some kind analogy we used was the in physics, the electromagnetic theory, the it is well known that the horizontal and vertical direction of Frenet coefficient equation is derived by the other previous researchers, but the problem is the GNS reflectometry, and GNS signal has the circular polarization wave, so we need to transfer this circular polarization to linear polarization. So we use several methods to transfer the polarization and then to get some linear Frenet coefficient and then linear Frenet coefficient and then electromagnetic field. So after some calculation, the we propose the quantitative relative dielectric constant, as you can see on the bottom of this slide. So it means that using the reflectivity from the GNS reflectometer receiver, we can calculate the dielectric constant. So after then, we haven't built any kind of model from this dielectric constant, but we will in our group we will use this dielectric constant value to predict the soil motion later on. So here's one field test. Unfortunately, we didn't took any photo while I'm taking a measurement on the land. So I bring this photo from when we took a test on the lake near the York University. So after this test, we will validate our soil moisture directly constant, because we'll validate directly constant using the soil moisture proof. So because there are so many type of soil moisture proof in the world, but beside among the method to calculate the soil in situ soil moisture measurement, the time domain reflectometry method also TDR method can predict the dielectric constant. So we use the soil moisture TDR method of soil moisture proof to validate our direct constant. Here is the one result. But unfortunately, our receiver has a limitation of measurement time as the 100 millisecond. We have to improve our receiver performance, so that will be done in the future. So in the left hand side, but this is just it will be good. Please think about this result as some initial performance test. So as in the left hand figure, this is the dielectric constant, relative quantitative dielectric constant using the method that our group developed. And then the right hand figure shows the dielectric constant from the soil moisture proof. So but the measurement time has very the in both two measurements there are huge difference about the measurement time. So we have to we improve our receiver and then try the similar experiment later on. Yeah, so here is the conclusion. So we build. I showed the what is the GNS reflectometry, and then theory of GNS reflectometry as a electromagnetic scattering theory, and then we built our FPGA-based GNS receiver in York University. So later on, we will build or we'll improve our receiver and then trying to put our receiver on the UAV and the airplane and the satellite to get the soil moisture, and then we will apply this our data to another application. Yep, this is the end of my presentation. Thank you for listening.
Okay, we have some feedback. All right. Yeah, so thank you for the presentation. I think this is quite an exciting topic. Do you have anyone with questions here? We have definitely a few minutes or 10 minutes or so to ask questions if you like.
Go ahead. You can first.
Maybe I can get started. So just to clarify, so right now you're doing these field tests, and the idea would eventually to be some kind of microsatellite or something in space that would do this for the entire globe?
Yes.
Can you hear me?
Hello?
I think we're muted right now.
Is the room muted? Because I think you're locked up.
Oh, wait a second. Can you hear me?
Hello?
Hello?
Go to the top bar there. There was that little drop down menu. We're not.
Yeah.
No, it's saying.
No.
Oh yeah. Okay. So.
So maybe it's on their end.
Yeah.
Can anyone hear us?
Hello, can anyone hear?
I think so.
Yeah.
Can the rest of us
I can hear everyone.
hear me?
Okay.
I'm hearing.
Someone? No. Can you turn on your... Can you hear us here?
Yes, we can hear you.
Thumbs up. We can't. We're not visible. So if you give them a thumbs up, yeah.
There's something in
Says I
the
can
chat
hear
that
everyone.
says I can hear everyone. So, probably hear it.
Yeah.
It looks stop the Zoom.
Oh
Yeah.
Okay.
And it says mute beside your.
Oh yeah. Can you press that maybe?
No,
Yeah.
Okay.
Nothing changing.
But yeah, no. Do you see the microphone?
Can you hear us still? I think he's frozen, no?
Yeah, I think
Yeah. That's right.
I can hear you, but Luke's microphone is frozen. Oh, okay.
Oh, he's frozen.
So he can hear, but he can't reply.
Okay. Can you just disconnect and reconnect?
Okay. Where?
Like, okay, I think you did, right?
Can they hear?
Hello?
I'm looking and it shows all of them on.
Well, everyone's on mute.
No, I think it's the button to make you.
No,
No, yeah, see, look, our microphone's is picking up.
Yeah,
sound.
like it's on the bottom left there.
can you chat to them and ask whether they can hear us now?
Yeah,
So
let me check.
it's next to the share button.
Yeah. Yeah. Maybe we should keep making
Yeah, we should
noises.
probably just keep talking.
Can you guys hear us?
Anyone?
Hi.
Yes.
Okay.
Oh.
we're audible.
Speaker.
All right, so back to questions then.
So we still can't hear you. And maybe we can do it in the way, if we can't figure it out, then I would just suggest that maybe you share your email address in here, I guess, or I can send out the emails and people can ask you questions in an email.
Yeah.
Maybe that's the best way forward at this point. Unless we can make it happen in the, okay. Yeah.
Yeah, I'm loading my email.
So everyone should, in the chat window, you can see the email address. So maybe the best way forward right now would be to simply ask questions that you may have had in an email, and then he can respond to you in writing. I think at this point, yeah. Then I would like let's thank the speaker again, and we're going to have the next session in a month from now. And feel free to use the opportunity to contact him and ask questions.